So, welcome to this talk about how to tame your robot. I'm Jiska, and...
Well, hi, I'm Fabian. And we'll show you a little bit around our journey of liberating some vacuum robots.
So, sometimes I have those projects, when you did reversing for quite a while, that are just lying somewhere on my hard disk, and people just ask me questions, and often those questions are like a fully separate project or like really out of scope. But this question was like pretty good. It was about the Nido robots I had analyzed back in 2018-19. And the person was asking me, can you help me reconfiguring and repairing one of the robots that I have? Like, he was just exchanging some components and needed some help there. So, to answer this, well, yes, I was helping him, but like, to understand everything that happens here, I have to tell you how a robot is born. Well, there's a factory. It comes outside of a factory. And the factory side has an identification number. And the robot itself also has then continued the name with the manufacturing date. And then there's, of course, multiple robots born on the same date, so they all have the same name. But they are still, you can, differentiate them because they also get a unique MAC address. So this makes the robot unique. Next step is it's Christmas, you get your robot. And, well, what do you do? What did you do? Okay, anyway, so it's Christmas, you get your robot, you unpack it. First thing it says, it opens Wi-Fi, and it's with this MAC address, so that's the Wi-Fi it opens. And now you have to pair it with an app. Did we break it? No, we did not break it. Not yet. We did not yet break the robot, only the animation. Alright, so you have the Wi-Fi, and you need the Nido app so that your robot can join the Wi-Fi. And this is the very first step, so you can use the app to directly talk to the robot, but it's super limited. So the only thing that it does is to set up, but afterwards everything happens over a cloud. Or basically it's even two clouds, so there's different servers either for accounts versus commands sent to the robot, but let's simplify that. It's like some cloud stuff. And this means that now, the whole robot it's bound, all the communication is bound to the Nido cloud, and all your data, like the floor plan and stuff, it's communicated to the app via the cloud, and it's nothing that you get directly from it. All of this is already locked in factory, so during the manufacturing process, the robot also has a certificate stored there. This makes it kind of secure, right? You can only talk to the Nido cloud, so to nobody else. Only with the correct certificates and only to exactly their servers. And when your robot breaks, I don't know, like 5 years of cleaning, it decides to retire, or maybe earlier it has a problem, then, well, what do? You have to pack it in a box and then leave it alone, send it back to a repair site. And of course, the repair site is, it's diagnosing the robot. Where is the... Here's, okay. So it's diagnosing the robot. They check what's with the robot, but it's nothing that you do yourself. So this happens only by Nido again. So this is again just blocked by the vendor, and they are of course authorized to do this and so on. And they only do the right stuff to your robot. Okay. So how do you now tame the robot? So there have been some projects before, but so there's pretty bold guidance. So first of all, your robot, it only talks to the Nido cloud, and only Nido can help you to repair it. So it has a serial interface, and this allows you some control, even on the very early non-connected series. For the very early series, they had some documentation for this even, and you can turn on, some test mode and then tell it to clean and so on. And some people on the internet had a really cool idea. So they said, well, first of all, so that's the command line. To see it. It's not so loud, right? Can I? It makes some sounds. So this is just an example of the serial interface. And some people on the internet had the nice idea that even for the non-connected models that don't have any cloud connection, you can make them connected to your own home IoT. And they have this cool project here on GitHub where you just solder on an ESP32 to your robot and then connect it to your home Wi-Fi and your home IoT directly on your own control with all your own scripts and send it those commands. And with this, you can already do the very basic stuff, like you can start a cleaning cycle, for example. So it does not only talk to Nido's cloud, and I mean, you can also do this, of course, to the more modern ones that talk to the cloud. You could still use the serial interface and lock out the other cloud. But yeah, it's still quite limited, and there is a lot of commands that are still locked because only Nido can do the diagnose and repair part, and that's stuff that you by default cannot reconfigure. And these are authorized commands, and those authorized commands, they are like there's a help menu, but they are hidden from the help menu even. So even if you have a newer robot, then you would get commands, but it's not the full command list. And even when you like randomly guess a command, then it would say, no, I need a valid key, or maybe it just does nothing. That depends. It's like handcrafted depending on the command. And then after 5 failed attempts, even if you would give it the correct key, it would just say it was incorrect. So it kind of locks that. You have to reboot, then this is reset, but it prevents a bit of the brute forcing. So I was like, okay, how can we look into that? Well, as I said in previous research, there was a bypass that I found. So the robot has a bootloader. That is so. Usually what should happen is that there is a secure boot and some certificate is stored somewhere that decrypts the firmware, and then only this firmware can boot. But before there is a bootloader, and in this bootloader you can also, at least in the old one, upload your own firmware, and this is then booted from RAM. And what I did was I sent another firmware image that is just loaded to another address in memory as the original firmware, and I just rebooted it, and the RAM is not reset, so you can just reboot and then read from the other memory range what is still there from the booted image. It doesn't give you exactly an image that would still boot because there's some flags set differently after booting in the image, but it is sufficient to unpack all the files on it. And so I had the firmware lying around just from this attack step. And yeah, that's enough to then look into the key commands.
And basically, this is where I came in, and I started looking at this firmware and trying to figure out what those keys are. Jiska was just asked me like, "Hey, how does that work? What's happening behind the scenes there?" And I can't keep my hands off some firmware, so I started loading it up in my favorite disassembler and starting to take a look. So I'll just guide you through some of the steps that I did there, just live right now here, and explain some of my process as I go along. So we'll start out just by the blank firmware. No reverse engineering done on this before here. There are some things that are changed in here just so that we don't leak any key material. But apart from that, it's pretty much just what we got of the robot. So we'll start out by just opening this in Binary Ninja. If we open it, it'll just put us, and it'll take a second to analyze. And maybe you remember that we talked about there was a message. You probably can't read this, right? So yeah, I can. Okay, I'll just one second. Rescale. Go. There you go. So maybe this is more readable for everyone here. Is that better? there it is. Is this better? Wonderful. Okay, so maybe you remembered there was an error message that was displayed, that was printed by the robot when we type in an invalid security key. It just said invalid security key. So that's a really good starting point, because, well, if we figure out where that's printed, we'll figure out where the security key is checked. So I'll just search in the strings, invalid security key. I'll find that, and I'll find that in memory here. I'll cross-reference where that's being used. And if I look where that's being used, I can see here, this seems to be printing invalid security key. So let's follow up where that's being printed. That's being printed here in R00. And R0 is the return value of this function. So this function obviously is something like check secure. I can't see underneath the microphone, so I'll just move this like this. I hope you can still hear me well. I'll just call this check security key. Yep, perfect. So, like this, we can already find the interesting functionality, and when we look in there, this thing is pretty interesting. We have a loop here, and that loop here does some string comparisons. This first string comparison seems to be looking at a structure that's of size OX24, because we increase that every time we iterate through the loop, and there's a loop counter here that exits when we hit 5. So we seem to have 5 different structures here that are of size OX24. So let's go ahead and look at where this comes from. If we go here, we can start seeing there's apparently some data here. So let's investigate that. We'll start out by defining the structure and saying, okay, we know it's OX24 big. And then we can also just tell Binary Ninja that the data here is of that structure, and then we have 5 of them. So I'll just say that. And then with the next thing we can see is there seem to be 2 things at the beginning of the structure that look like pointers. So I'll start out by telling Binary Ninja, hey, there's a pointer here, and when I do that, it dereferences it, and we can see there is some string data here. So let's go ahead and say, okay, this is a char pointer. And the next thing, just assuming that's also going to be a char pointer, so I'll just also call this a char pointer. And then there's also some other string data at that address. The rest of the interesting data doesn't look that interesting here for us, but this already helps us understand a bit. Okay, we apparently have these 5 things. They have some things at the beginning called looking like default ID, set QA state, set manufacturing code, command line service, or manual drive key. So these identifiers seem to be something that are important, or maybe categories of keys that we can use for different functionality. So looking farther down, we can see that there are 2 different cases which this function could return. Remember, this is the function that checks the security key, and if we return 0, we will be printing that error message. So we don't want to return 0. So there is a branch here, in which case we will not be sending 0. So this is conditional on another string comparison. Again, here, bit different syntax. Left shift by 2, that's a multiplication by 4. And then there's another multiplication by 9. If we do 4 times 9, we get OX24 in hex. So again, we're looking at the structure, and if we look at where this address points, that just points us into into these 0 bytes that we have in our structures. So we're comparing the data that is at these 0 bytes here to something that we're inputting, and we're doing a case insensitive comparison. So for some reason, this looks a lot like this area in memory is what will be holding our key, the key that we will check against. So when I saw this, I thought like, well, that can't be right. I mean, the keys can't all just be zeros. And trying that out, yeah, it didn't work. So something must be writing to that memory to make sure to tell us, this is what the key. Where is this key calculated? When is it put into memory? And this is what we'll look at now. So again, we're going to just look at what else is accessing this memory. And there's a couple of other places. One of them is this place, and this place, just digging down some further functions, we can go here, again, we see a loop with a ×9 and the left shift by 2, accessing this memory. So again, we're accessing each of these structures and accessing the empty space in each of those structures. And then we're calling a function on that. And if we look in that function, that has some really interesting log print messaging, or log message here. It says do encryption. So this is the juicy bit. So just by going on and following the data flow from our error message all the way to what else is accessing that memory, we can figure out this is the juicy bit, this is where the cryptography happens, and this is what we want to understand. And looking further, we can see that there's a debug print which prints a robot serial number. And if we look at the logs through the serial number, we'll see that the serial number is actually the MAC address that Jiska pointed out is different for every robot. So they're reusing the MAC address here, and this MAC address is somehow being used in this cryptography. Going further, we see two different functions which we don't understand yet, and then there's an sprintf which is targeting the output. So following the arguments that are put into this function, we can see this sprintf is hex printing something, and it's XORing something here, and the thing that it's XORing. So let's just check out what it could be XORing. This is the serial number. And just following that, okay, it's XORing the serial number at some offset I, or the ith character of each serial number. It's XORing that with something that we have on the stack here. And this is just some decompilation error. What we will see in the end is this is basically this variable, which is on the stack, which is calculated by these two functions. So basically we're doing some setup, then we're XORing that with the robot's MAC address, and then we're printing that out as hex, and then finally we're also appending a specific character just to the end, maybe like a checksum. So this is some hand-rolled stuff that we're just looking at here. So looking further down, we just skipped over these two functions, so let's take a closer look at those. Don't want to rename them, I want to jump into them. So the first one basically has some loop, it does some division. If we would reverse engineer that further, we would see that it's a modulo, and the other one we go in there. That basically also has two loops that are after each other. I'm not going to go into too much detail because I'll explain these functions closely. But right now I'm looking at these and I say, like, what the hell is this? I have no clue. I'm not a cryptographer. I don't even recognize most crypto when I'm reverse engineering things because I have signatures that tell me this sometimes. So I'm confused. And with that, I decide that, well, this is where the logic is. I know what's going into it. I know it's the MAC address that's going into it. And it's the key, or it's the other part following that that's going into this function. The other information is coming from this second field, which is apparently some initialization data that flows into it. So I know the only inputs I'm looking at is some static data that's in this binary. Right now, here I've replaced that with a few other values just to not leak that. And there's some other information, which is the MAC address. These are the only two inputs that are going into this cryptography, and then out of that, I'm getting some key that is string compared against. So with that, I don't know. Let's try to build keygen and try to figure out how we can find those secure keys. So the first thing that comes to mind when looking at firmware, and there's some interesting functionality that you can trigger, is how about we can run it in an emulator. And so one thing about me is I'm lazy. I don't like implementing emulators all over again when I'm just looking at a small thing. It's tedious. You have to sometimes implement memory mapping, implement a loader, all those kinds of things. And I was feeling lazy. I didn't want to do that. So implement an emulator today. How about I just re-implement the whole thing? I take the lifted decompilation and just take that and rewrite it in Python. I did that, didn't work. Gave me wrong results, so I did something wrong apparently there as well. So, and I sat down and thought like, well, what can I do now? And then, you know what? How about I do a bit of both? I'll run it in an emulator, but only the bits that I'm interested in. I'm not gonna care about all the rest. So, lazy me said, you know what? I'll just copy paste the disassembly into a file like this. I'll rename the functions, and by that time I understood that one function did some swapping of rows in some table, and I just copy pasted it. I changed the loop targets and the label and made them labels in here. Copied the other function that was doing something that looked like shuffling. I didn't know what it does, so yeah, again, I just changed the things that look like jumps to not have addresses but labels in there. And then I wrote some C code. And the C code basically does this, is just the do encryption function, has some of the table up there. It takes the MAC address from as an argument. And then I just call these two functions after each other. I do the printf to make it a hex string. I copy over that byte at that point and append it. And then, you know what? This worked. I compiled this together. I linked these two files together. I ran it on an ARM machine. It just works. I ran it under QEMU user mode. It worked. So I had my function in keygen, but I still didn't understand what these functions are. I was still utterly confused. And then I thought, like, I could start debugging this code now. And I said, like, yeah, no, I'm too lazy to attach a debugger. I'm just going to put printf all over the place. And then I wrote these two little functions, which are basically printfs that I can call from the assembly, and I put them in there, and I compared it with my Python implementation, and I tweaked that until I got the same thing in every iteration. I guess maybe just using a debugger would have been faster, but this was lazy me. And then, in the end, I had a pure Python implementation of the cryptography, just the function. It gave me the same results. And I thought, like, well, they can't have invented this, right? I didn't recognize it. I had no clue what it was. So, maybe some other people do. I thought, ask some friends. I was just typing in IRC, said, here, I pasted this somewhere. Yeah. Does anyone recognize this? Okay, a couple of you. Just type this into IRC, pasted it. Does anyone recognize that crypto? No? Oh, yeah, didn't take long. Someone answered, that's RC4. Said, yeah, thanks. Okay, I guess I reverse engineered and re-implemented RC4. Go me. Then, yeah, well, other people did that as well, apparently, lots of times. And then, yeah, then Sar pointed out, well, that happens all the time. Yeah, and that was basically okay. Figured out, okay, there's RC4, static key, just XORed with a MAC address. And that's how we figured out how to find those keys. So pretty straightforward from there on. So with that, what can we do with this now?
So yeah, the idea is to have. Yes. Awesome. Yeah. So to no longer have these walled gardens, because we now can run like all the commands on the robot. And the first thing I have to tell you is better have a backup. Because like first thing I did was not making a backup, but I still had a few things up back in my console that helped me to rescue the robot after changing settings. So if you want to play with this, really back up all the settings and maybe don't depend too much on your robot. It's a bit risky to do this. So yeah, there is really all the settings, all the calibration values in there, and you could reset them. Oh, that was so. Then the next thing is you can get the Wi-Fi settings. I mean, yeah, not too interesting, but apparently the person who implemented Wi-Fi also was struggling a lot with setting up Wi-Fi, and so the get Wi-Fi status does not only have this WPA config, but it also has access to the whole system log. So you can see the whole system log with the slog info command, but only the last few lines. But what you can do there is it also has a filter command, so you can filter for certain strings in there, and it's really helpful with debugging. So when I messed some settings up to see where my robot hangs now, this was super helpful. What? Why is... Okay. So this is how the system logs looks like. In the beginning, it does not even have a time. Then it sets the time. Then you can see it connects to the cloud and so on. And in all those steps, if some settings were wrong and it fails, you would see it directly. And so the first command I tried was, I just reset the settings because, I mean, I didn't care about my cloud connections. I was like, set config, reset all, And so what do you think happens? It just sets all the values to -1. So not a default value, but -1. And this also means that the brush now does no longer go with 1,400 RPM, but it now goes with -1 RPM, which just means it doesn't start anymore. The robot does not even clean when you say reset all. And this is how you can screw up the robot. And so I had a get version somewhere back in my history, and also some of settings in the database, and it was sufficient to restore the settings to make it clean again, but it was like, yes, I hacked it. Oh no, I pricked it. Also something that you can do, so there's different models of the robot, and they also differ in what the cleaning settings are, and one of those settings is how much energy is used for the vacuum power, what is in the echo mode, what is in the turbo mode. So echo mode might also just be 50%, for example. And in the app, you can only set these two settings, but not a percentage of the cleaning power. So you can change that, for example, on the command line. And also something, is this animated? No, but why is it? Okay, anyway. Yeah, it doesn't matter. So there should be not just a green dot, but an animation. Anyway, so if you can configure the Wi-Fi, and the best thing about configuring the Wi-Fi is you can fully disable the Wi-Fi, which also means when your robot reboots and the Wi-Fi is not set, then for half an hour it would say, yeah, I'm an Edo, can you please, is there an app, help me? And this, just disabling Wi-Fi is a cool thing. And also something where I think, again, the person who implemented Wi-Fi was really struggling, it has a telnet option. And this really means it starts a telnet daemon, but on port 23, and I think on the version of the robot that I have, there is no permission to start something on port 23, it's no longer running as root or something, so it didn't work for me, but it might work on some very old models that haven't seen an update for a long time, I guess. So someone had kind of a backdoor to, first of all, get all syslog with the get Wi-Fi config, and then also do everything on a shell with the set Wi-Fi. And yeah, then there is the next thing, super fun. You can recalibrate the sensors. But you should recalibrate the sensors while the robot is in a special box, with special colors and special distances. And if you do this wrong, then your robot fall sensor and stuff might no longer work, which means it could fall on a person. But then again, if you do repairs on your robot and do something on the sensors, you might have to recalibrate them. So this whole procedure of how you recalibrate it, what you need, is not documented, and it essentially prevents people from really repairing the robot. So I mean, I now have my calibration values from the config database, and I could probably set something in that range if it breaks. but it would be nice if there would be documentation for this whole part of how to calibrate the sensor on a broken robot and what is a valid sensor range for certain sensors. And you can tune your robot. You can just say, yes, I just bought it yesterday. So it looks young again. And also, you can also say we have a new battery. So you might actually need that when you put in a new battery. But you could also say it would have one. Don't know what happens there then. So there is a couple of lessons learned because so far this was just, we reversed it, we hacked it, we set some config stuff. But what can we learn from this? So first of all, modern IoT devices, you can still get them under your control. It's just, so it's possible. It's just a lot more work. And I think I spent more time unbricking the robot than the whole, how do we set a key? So, because, it's not working, and you're there, you're just, you cannot look up anything, and it doesn't start again. I think on the reset, it was not just the brushes reset, but also the whole manufacturing ID was reset, and I don't know what, I really had to figure out all the settings and how they go into the robot and go through the boot log. So Nido sets the bar quite high. So first of all, there's QNX. I mean, it can be secure or not so secure. That depends on the QNX configuration, but it's a weird operating system. Not many people know it. They protected the interfaces with some key mechanism and everything. They have individual encryption keys for the robots, so I could not just send in my robot with a fake firmware and they connected, or I don't know, a keylogger or something. It wouldn't work. So there's a lot of thought in the process of what they built and how they did it. There's also safety implications. So this whole sensor recalibration can be really dangerous if the robot falls on a person, for example. But then again, it would also be nice to have precise instructions how to do the calibration in order to be able to repair it without Nido. And how do we mitigate this? I think a lot of this is common in a lot of IoT products because the security is only implemented inside the robot. So all the checks, if this is an authorized command, it's only on the robot side. And yes, the ASCII algorithm prevents from attacks if you assume that the firmware on the device is never ever extracted. But once, even if they do an update or something, let's say there's a QNX Wi-Fi remote code execution bug and someone gets into the robot, gets into the firmware, then the same problem could happen again. Of course, you can put more obfuscation into it, more checks, stronger crypto, but as long as the check is only client-side, you would always end up with the problem. And that's not just a Nido problem, that's really a very general IoT device problem. Because if you want to make this secure, then you have to build in something where you store certain certificates and keys in something like an HSM, and then you have some authorization, and then you have this also on the server side, I don't know, there's a server that authorizes all of this that is going on to really check nothing happens to the device without the consent of the manufacturer. And this is a very big overhead that is usually not in scope of an IoT product. And so next question is when is there the key generator? So you saw those nice things, never gonna give you up, but that's not the real secret stored in the firmware. There's others. And so the thing is that Nido still needs to fix this. So they also have to not just roll out a new firmware, but also all the repair sites need to get now a new key generator with new stuff in there. And this is why it might take, I don't know, probably 3 months, maybe a bit more. And once they are done with this, we will be able to, push out something where you can generate the keys if you are willing to stay on an insecure old firmware and don't connect your robot to the cloud. So stay tuned for this if you want to hack your robots. And then there is a special thanks page. So first of all, Nido was really nice during the disclosure and asked us questions, all the stuff that you need to know to fix this. Then persons on the internet, like the person asking me, like, how does this work? I want to repair my robot. And also...
And yeah, big thanks to M for just pointing out, hey, that's RC4. I wouldn't have guessed that. And I think with that, we're at the end of our talk. And in case you have any questions, we take them now.
Thanks, guys. We actually, I think first time today we have about 5 minutes for questions if someone has some. Yes.
Is it possible to run a custom firmware on the device after you hacked it?
So with the old bootloader patch, or the bootloader hack that I had, so with the old bootloader hack that I had, yes. I'm not sure, because for the new one, like the secure boot is something in that chip. So I think you would have to hack the secure boot of the chip. Yeah. Maybe if you manage to downgrade to an older firmware version or something like that. Okay. Yeah, anyway, so I think you get your wallet, yeah. So I'm not sure if it applies to this, but I think the file system you're booted into is like read-write. So if you get code execution, I mean the command line interface is no code execution on the robot, it's only the interface. But if you get code execution, you can swap files, I think. Yeah, it's kind of getting your own firmware onto it.
And yeah, just to note, none of the commands that are available using the security keys allow you to reboot your own firmware. So those commands that are protected like that, they, as far as we can see, they're just for manufacturing and debugging purposes or repair purposes. So they don't allow you to do that.
So there is a command to put new firmware onto it, but it would still get checked. So that's the thing. You can, like the firmware made by Nido, you can install it with the commands. Did you have a question? Or? No.
Do we have any other questions today? Okay, on the back. Yeah.
Given that the secret key is XORed with the MAC address, and the MAC address is publicly, you can just find on the network, doesn't that mean once you have one device, that means essentially you can discover, you have the secret key, you could get the secret key for any device at all.
Yes.
Just being by on the same network as that device.
Yes. If you had a valid secret key, then yes, you could do that. You could discover the value that the post RC4.
Right.
And then you could just XOR that, and you would be able to find the constant secret, which is the same for all robots. Yes. But the issue is here, those secret keys aren't given out to anyone, so only the repair shops have those.
And you.
And we, yes.
And also, all the secret keys are going to be related because the IEEE hands out the manufacturing code to Nido, and so
yes.
only the bottom bytes are going to change.
Yes.
And they're all sequential too.
Yes.
Okay.
Last question. Yes, please.
Yeah, was the firmware signed or somehow it's checked? Yes.
So yeah, the firmware blob is signed and encrypted. So from the firmware blob itself, you cannot get anything. There is, I think, firmware blobs on the internet because you can intercept the URL when the app updates the robot. But they are encrypted for the key in the secure boot, so for the chip, and nothing that you would get out. Mm-hmm. And that's why you need an attack like the one that I said in the bootloader, where you have some bypass, for example.
Okay. And while you were debugging the RC4, you said that you put some printfs inside, yes? So how you did it? Did you patch the firmware or what?
No. Again, I copied and pasted the disassembly from that into an assembly file, and I ran this on my computer.
Oh,
or well, I ran it on an ARM computer, which isn't fine right now, but yes. So I guess this is cheap rehosting by just copy pasting the code.
Okay.
Okay, thank you guys. Give a warm round of applause to Jiska and Fabian.